Okay, so welcome. So what we're going to do today is myself and later Mark Sumner are going to be running a revision session. So Mark's going to be coming in to run the second part of the session. So we're going to split it across our topics, but we're going to cover some things, and I'm just going to cover some basic things about the exam. In this module, we have a 2-hour exam covering machines and drives topics. So obviously you don't know when that is. That'll be scheduled exactly at some point soon, but that's going to be in the exam period in January. So it's an 8-question exam, 8 10-mark questions, 4 from me, 4 from Mark Sumner. So my question topics are distributed across 4 areas. So I'll have a question on magnetics and machine basics, which is the things you did with me in the first couple of weeks. I'll have a question on AC induction motors, and then basically something else on induction motors. So in total there'll be 2 questions covering induction motors as well as some of the fundamental AC field stuff. So not covering synchronous. This is one of the important points of the exam. So the synchronous machines material isn't covered in the exam. Obviously you're doing, or if you're here hopefully have done and submitted a coursework on this. So we don't cover synchronous machines in that exam directly. The places where they might still crop up is in comparison. So you might be asked to talk about induction machines in comparison with synchronous, or reluctance machines in comparison with synchronous. So those are the first 3 questions. Question 4 from my side will be based around 2 topics: switch reluctance motors, which you've done with Tianji, and thermal effects, which we did last week. So that's our topic split. So there's a reasonable amount to revise there across those different topic areas. So what I'm going to do in a little bit is just to recap some material. I wouldn't suggest you just go over the things I've recapped, but this is just picking out key points, talking about key areas. And I'll also just briefly pull up some past papers. If you look on Moodle, we have the last 3 years of past exam papers, which can give you an indication of how exams are structured, how questions are set out. It is important not to just revise from the past papers. You can't expect this year's exam paper to be exactly the same. There will be things that you haven't seen before in past papers, but if you know the theory, you should be able to answer it. Another important exam question, and this is something that if you're an undergraduate, I probably said to you when I taught you in year 1, is be careful about exam theory. So things like this, so we have 8 independent questions in this exam. Make sure that you go through the exam, make sure you try and answer all the questions. And what I mean by this is if you spend an hour trying to answer question 3 and then don't address questions 7 and 8, that's put you in a really, really difficult position. If you make sure you go through that exam paper, try and answer all the questions, what you'll find is that there's a mix of challenge in each question. There'll be some questions that are easier to answer, some questions that are harder to answer. So be aware of the time you're taking, be aware of the fact that you've got 8 questions, so you've got a certain amount of time. You know, you've got 15 minutes of time effectively to spend on each question. If a question's taking you longer than that, put a pin in it, move on, look at another question, try and get those answers out. There's nothing worse than marking an exam paper and basically seeing someone's missed out on half the paper because they spent ages trying to solve a more difficult problem in the early part of the paper. So make sure you address everything, make sure you answer everything you can in that paper, and ultimately make sure you're prepared. Make sure you go over these techniques, make sure you understand the material. As I've said, past papers are a good guide. They aren't exhaustive, but they'll give you a good indication. If you recognise most of the material on there, you're in a good position to succeed. The material should all be online, the notes are all there. If you have questions around exams, myself and Mark will be available at some points, but bear in mind, we will both be having a break over the Christmas period. Personally, from my point of view, I'm away from the middle of next week till the first week of January, so you won't get instant answers to questions. So make sure you study the material, make sure you go through things. That's the sort of basic structure. So, as I said, next I'm pulling out some key topics of the kind of material that's important. So from the first couple of weeks of material, We talked about some things. So these are sort of overall broad topics we covered. So things like topologies, going from first to the second and third generation of machines. We talked about some typical applications, challenges, requirements, the kind of things that we actually need to know to use machines. We talked about magnetic circuits, relationships in these, and how we can actually do calculations to solve magnetic circuits in the same way as electrical circuits. We discussed magnetic materials. We talked about ferromagnetics, BH curves, lamination hysteresis, permanent magnets and how those behave. We defined that fundamental magnetic energy and force that we get from a field in a gap. And we defined those two key principles of force production and voltage induction. We defined this ideal torque equation, which gives us the ideal torque we can get from any machine, and we went over some fundamental power concepts of efficiency, rating, connection. So just to drop back into these, as I've said, these are all things we've taught before, but I'm just going to flag some of these up as useful things to know and to understand. So we talked about the evolution of machines from first to third generation, where our first generation were simple copper and iron type machines. These are the kind that have been around for hundreds of years, up to the permanent magnet type machine, which took advantage of improvements in permanent magnet material to do some interesting things, to get permanent magnet AC machines and brushed machines. And then finally to our third generation control reliant machines, which we've been working on, especially in the latter part of this course. So things like switch reluctance machines and permanent magnet DC and AC machines, which are entirely enabled by drives and control and typically rely entirely on those power electronics to be able to operate. We talked about a number of applications, so obviously not going to revisit this in detail, but sometimes questions come up around applications, talking about how machines will be applied to particular applications. This is something that partly comes up in my material and partly comes up in Mark's material, but talking about some of these applications we learned about, the types of machines that are used, and why they're used in very broad strokes, you know, why certain types of systems and machines are more appropriate. We define these magnetic circuit relationships. So there's a lot of magnetic circuit relationships, but the first sort of left-hand side of that line is the sort of fundamental part, because that governs the behaviour of magnetic circuits. It tells us how we get from current flowing in a circuit to the magnetomotive force induced to the H and the B, so our field intensity H and our flux density B, which can be worked back to flux. So that's how we can solve these magnetic problems and work out what's actually happening in the magnetic circuit of a machine. And many of these are other sort of guidelines, so these are the kind of things that have come up at various points around force production, around magnetic circuits. So talking magnetic circuits, so these were those sort of fundamental rules around magnetic circuits. So our magnetomotive force is equal to current times turns, which is equal to field intensity times length. And by equating those together, we can relate the electrical domain to the magnetic domain and work out what kind of field we're producing from a given current in a given coil, for example. We have a relationship between flux density and field intensity, B equals mu naught mu RH, which represents the flux density we get from actually driving a field through a material. And that's dependent on what the material is made up of, which is governed by that mu R permeability characteristic. We also discussed that link to magnetic and electric circuits, how we can take our MMF equals flux times magnetic reluctance and use it in the same way as we can use Ohm's law, V equals IR. And if we do that, we can draw out magnetic circuits, we can look at the paths for flux, we can apply all kinds of the circuit tools we've learned over the last few years to actually solve magnetic circuits in the same way we would electrical. We talked about magnetic materials and how we have these ferromagnetic materials that we very, very commonly use in machines because they give us a really good high permeability path, which is good at carrying magnetic flux. So we can use very, very little current to create a huge magnetic field. We have two fundamental types of these, hard and soft magnetic materials, and both have their uses. Our soft magnetic materials are easy to magnetise and demagnetise, so are good for magnetic cores and machines. Hard magnetic materials are difficult to magnetise, but they hold a lot of magnetisation in, so those are what we use for our permanent magnet materials. We also define a little bit the losses in these materials, how we have two sets of losses. We have a loss from eddy currents, currents circulating in the ferromagnetic material itself, and a loss from hysteresis, which is the loss behaviour of cycling these magnetic circuits. As we drive a flux change in them, we actually drive a physical change in the crystal domains, which manifests as heat and losses. And we can define these broad behaviours with a BH curve like this. And this is a way we can actually relate the field intensity H to the flux density B. And that comes back to that B equals mu naught mu R H curve and shows that effectively our relative permeability of a material changes as we drive more flux through it. So this is our fundamental magnetic material behaviour. But using these rules, using these characteristics, we can predict the loss of our magnetic material, and we can also predict what kind of flux density we'll get depending on what field we're driving into our magnetic circuit. We talked about permanent magnets. So these hard magnetic materials that we deliberately use to create a permanent magnet, these are very commonly used to give magnetic fields. They're very commonly used in machines. So some of the machines I talked about in those second and third generation rely on permanent magnets to give the field without using extra power. And they are very good for that. They give you very good power dense machines, but they have real limits. They have temperature limits, so the Curie limit beyond which they completely demagnetize. They are expensive, they are somewhat challenging to work with, but they do give you very good performances. And we have those sort of key characteristics, we have these key materials, and what we find is that our rare earth magnets, which we hear about in the news all the time, are by far the winners in terms of pure performance. They give you a high remnant flux density, so lots of flux in the default case. They're very hard to demagnetize in operation. They have a nice linear performance, which means even if you partially demagnetize them, they'll come back to the original point. And they're relatively temperature stable. So these are good permanent magnet materials overall. Then we talked about our principles of energy conversion. So in those first few weeks, we went to this sort of fundamental fact that machines are all about converting energy and work. So converting between electrical and mechanical forms. It could be generating electrical power from mechanical work, or it could be creating mechanical work from electrical power. But either way, you transfer it between those two domains, and the fundamental machine always follows this kind of pattern where you've got an electrical system and a mechanical system. You're transferring power through a coupling field of some kind, and each of these stages has a loss. We have electrical, mechanical, and magnetic losses, all of which we can define in order to define the behaviour of the machine. We came up with some fundamental expressions for magnetic stored energy and force, and this is something I think Tianji recapped with you last week. But we can define our magnetic energy stored in the air gap in terms of our flux density squared times the volume of the air gap over 2 mu naught, so 2 times the constant of free space permeability. And we can define the force that we're going to get. If we store a magnetic field in a gap, we get a force trying to get rid of that field and close the gap. That's our F equals B squared A over 2 mu naught. So they're two fundamental equations, but they're very useful in terms of solving magnetics challenges. We also talked about these forces, our Lorentz force, which is the force on a conductor in a field. And assuming all these things, the field, the current, the conductor are orthogonal, it comes to a very simple expression, F equals BIL. So this is something we actually applied in some examples. We showed how you can calculate forces, you can work out the behaviour of machines. And ultimately, machines' topologies get more complicated, but they're all relying on this same fundamental principle of Lorentz force in terms of the sort of standard machines. If we have a current through a conductor, if it's in a magnetic field, we'll get a force. And then the other side of the coin, based on Faraday's law, is our expression for induced EMF. Our induced EMF we can find is equal to B times L times U. So EMF is equal to the flux density times the length of the conductor times the velocity of movement through that. So that's just an expression of Faraday's law, but once again that's the other side of our coin. Just like we've talked about how we can get a mechanical force from an electrical system, this tells us how we can get electrical potential and ultimately electrical work out of a mechanical motion of a conductor through a gap. And then one of the most important things in both of these is Lenz's law. So Lenz's law is an expression of conservation of energy that basically says all these things are going to oppose one another. So if we're moving a conductor through a field, for example, we'll get a mechanical force opposing motion. And if we can keep that conductor working, it implies we're putting in mechanical force with motion and putting in mechanical work. And it's the same the other way around. We're going to induce a current flow due to change in field, so if we're getting a mechanical force out, we have to be putting electrical energy in. So this is just keeping the balance of the universe, showing us how we have to be putting in electrical work to get mechanical work out, and vice versa. We talked about some of the fundamentals, so our ideal torque equation. So the ideal torque equation is 2 times electrical loading times magnetic loading times volume. In reality, we can replace that 2 with a factor that represents the actual behaviour of the machine. But both of these characteristics can be defined. Our electrical loading can be defined with the number of conductors per unit periphery. Our magnetic loading is the average flux density over a pole. We also talked about common things like conductors being placed in slots. This lets us get a better magnetic circuit, but we still get that full force equivalent behaviour. We still get force equal to F equals BIL. And some of the limits on this, voltage being limited by insulation, current limited by temperature rise. And we discussed a little thing around three-phase connections. So connections and also power things. So these are all things that you should have learned before you encountered this third year module, but just things like we recapped the definition of efficiency, we talked about power factor as the total amount of power that's actually consumed in some way. We talked about that concept of rating, how long a machine can operate for without overheating, and a little bit about connection patterns. So our star and delta that let us change the potential across each phase of our machine without rebuilding our machine. So that's just recapping those first couple of weeks of my material. So the next thing I'll talk about is the induction machine and AC travelling wave material that we talked about. So these were the fundamental topics that we covered in AC and induction machines. So we started out discussing that principle of AC fields, as well as synchronous speed, variation in number of poles, and how we use things like winding factor to try and get a better representation of our AC waveform. We introduced the induction machine principle of operation and that concept of slip, how we have a difference in speed between the rotation of the rotor and its conductors and the rotation of the field, and this induces EMF, induces current flow. We talked about our equivalent circuits and performance prediction, and we also looked at variation of performance with things like rotor resistance, how this really changes the characteristic of our machine. We discussed those testing methods, how we can use those simple equations to populate a circuit and to solve it, and performance calculation using power flow and losses, as well as some things about starting and performance improvement. So in AC machines, our fundamental principle is that we want to build some kind of travelling field. So going back to the general AC machine principle stuff that we did just before synchronous machines, we talked about how we're trying to get the same kind of behaviours that let us have a time-varying current distribution and field distribution around our air gap. So our fundamental AC machine has two sinusoidal distributions. It has a set of three-phase currents distributed sinusoidally in time, so those are time-varying currents, and it has a set of windings distributed sinusoidally in space. So in its simplest form, this is our sinusoidal distribution of currents. As we talked about, in real machines, the windings get more complex and get closer to a real sine wave. But either way, ideally, those are sinusoidally distributed in time and space. And what that gives us is something like this, a net travelling wave. If we look at the contribution of the MMF of each phase A, B and C, in each case we get an overall sinusoidal waveform, so something like this gold net waveform here. And as well as that, if we look at the behaviour over time, as our time steps on, we find that that waveform is actually travelling over time. So our field travels along the air gap of the machine, our current distributions, our flux densities are moving at a speed fixed by the frequency of excitation of the current. And this is a fact we exploit in induction machines, in synchronous machines, in some kinds of reluctance machines to give us travelling behaviour, to give us behaviour and output power. We talked about this factor of number of poles and how if we take two machines of the same length, if we introduce extra poles, so if we introduce extra phase windings, for example here we might have A minus B, C minus AB minus C. If we take that same pattern, the same number of turns, the same number of conductors, but split it into two repeating sections, starting with A there and continuing with A there, what we find is for the same length of machine, we get half of the field speed in the air gap. So we get our synchronous speed, the speed of travel of the field, being related by the number of pole pairs to the electrical speed. So if we put in a certain frequency into two machines, one of which has 2 pole pairs, the other of which has 4 pole pairs, the field of the machine with 4 pole pairs travels at half the effective speed. So this is a way we can actually manipulate the speed of our machines, and it's a very common way we see different speed machines develop for the market for different applications without having to go to variable speed drives and other more expensive solutions. Then we talked about the winding factor. So we have this approach we showed before where we assume our winding is a sinusoid, but in real cases that isn't quite right. That winding is made up of a set of conductors in slots, so it's always going to have a certain amount of granularity. It's never going to give you a perfect sinusoid. You can get quite close to a perfect sinusoid, but it's never going to be perfect. And the winding factor tries to account for that by reducing that fundamental MMF waveform, by reducing the current distribution by a certain factor based on the design of the winding. So it's something that's very commonly applied to actually give us a reduced behaviour, and that's the factor that ultimately feeds into torque and power production, giving us a net reduction in power produced. So moving on from general AC windings into induction machines, the key characteristics of an induction machine are they don't have any saliency, they don't have huge variations in the magnetic path with rotor position, they have stator and rotor conductors, so they need some kind of path on the rotor for currents to flow. The stator is going to be fed with an AC supply, while the rotor conductors are short-circuited to allow the circulation of currents. So we have a good visual representation on the top right there, showing basically a 4-pole machine with 4 magnetic poles there. You can see the flux lines linking the stator and the rotor, and you can just about notice that actually that rotor is moving slower than the stator. So for the fundamental principle of operation, if that rotor is moving at any speed other than the same speed as the stator field, it's going to see a change in the magnetic flux. If it has a change in magnetic flux, it has d phi by dt by Lenz's law, it says it should, by Faraday's law and Lenz's law, it says it should have an induced current, and that current's going to produce a force which is trying to synchronize its speed with that field. It's ultimately trying to minimize that change. So we induce that EMF, that can cause a current to flow in these short-circuited cage bars, and those currents give us a force trying to synchronize the speed of the rotor to the speed of the stator. So the main form of induction motor is the cage rotor. We can get more complex forms, but this is the typical one that we find. And this is very widely used. It's a simple, robust industrial type of motor. And this is our fundamental principle of operation. As I've said, we get an induced EMF in our rotor based on dφ by dt. So as long as there is a difference in speed between the rotating field and the rotor, we're going to have some induced EMF and we're going to have some kind of force production. So this machine will give you some kind of force output at any speed other than when the rotor is entirely synchronized with the stator. We actually have a factor that governs this. Because this is an important factor, we have a factor called slip, which gives us the difference in speed between the synchronous speed of the rotating field and the rotational speed of the rotor. So our slip is synchronous speed minus rotating speed divided by synchronous speed. So that gives us a basic factor that's going to be 1 when our rotor is stationary at stall and our field is moving at whatever speed, and our slip is going to be 0 if our rotor is moving at the same speed as our field. And this is a good governing factor that's included in a lot of our equations that represents very well our power flow, our power transfer, and our machine behaviour when we get to equivalent circuits. So in our equivalent circuit, we went through how we developed this from transformer theory. So we start out with separate circuits for the stator and rotor, accounting for power that's linked between the two. But ultimately, because the rotor is a closed loop, because it isn't linked to anything else, we can then refer all those rotor quantities back to the stator and come up with an equivalent circuit like this, with a few key components. We have stator resistance and leakage reactance. These two components, RS and XS. We have our magnetising branch components. RM represents those iron losses we talked about, hysteresis and eddy current, while XM represents the magnetic field linking the stator and rotor. We have a second leakage component in the referred rotor circuit, JXR, representing the leakage of the current flowing through those rotor conductors. And then we have the resistive components on the rotor. So as we talked about, there's two ways to represent these. In this full form, we represent these as two resistances. A pure rotor resistance, which gives us a loss, and rotor resistance 1 minus slip over slip, which represents our output power. We sometimes also sum these both together into one global component, RR divided by S, which represents the total power into the rotor. And both of these ways are accurate. It's just that the method with the two resistances is quite neat in that it splits directly between the loss-producing component and the component that represents power into or out of our induction motor. So this is our fundamental equivalent circuit, or full equivalent circuit. Now we also have a second equivalent circuit that's very commonly used in induction motors. And in the approximate equivalent circuit, the only difference is we take that magnetising branch, the RM and XM, and we move them from this point here between stator and rotor to this point here across the supply. So this introduces a small error because the voltage across that magnetising branch is going to be slightly incorrect. It's going to slightly affect the behaviour of the machine, but typically not by very much. But the key advantage of this method is that you can then do very simple calculations because you have the whole supply potential directly across the magnetising branch and that same supply potential directly across the rotor branch. So it simplifies our analysis right down in order to make our machine much easier to solve. So this is something that we use very commonly because it gives us a better, simpler representation of our circuit. It introduces a small error, but we can generally live with that. So we also talked a little bit about performance and torque. So using that equivalent circuit simplified, we can do some fairly simple methodology that basically says we can work out quite simply what's going on in our circuit. We have a way to calculate the rotor branch current and the magnetizing branch current, and then using the magnitude of the rotor branch current, we can actually work out the power across those components. So we can take 3 IR squared R1 minus S over S times 1 over rotational velocity. So remember, that's the component here representing our real output power, and that will give us our torque. If we multiply back up by that velocity, that will give us our output power. But we have a direct way to work out the torque in our machine. We can also work this out in terms of the overall air gap power. So this is using that rotor resistance over S as our total, which will give us our total power into the rotor, some of which is losses, some of which is output. And if we divide that by our electrical synchronous speed, we get our actual output power again. So 2 different ways, but both of them should give us the torque we're developing in our machine. So one of the reasons we give you 2 methods is that in some cases we don't actually have any rotational speed. So at standstill we do produce force and torque, but we don't have any rotational speed. So we need a method that actually uses the field speed rather than the synchronous speed. But this is a useful measure because if we use this methodology, it'll actually tell us if a machine can start with a given load. If we have a certain fixed load torque, then we can use this to calculate our torque at standstill, and that tells us if our machine will even be able to start with the mechanical load it's driving. We also looked at acceleration, how we have a difference in torque between the mechanical load TL and the output torque. And effectively our machine has an acceleration behaviour. As long as it has more torque available than the load torque, this difference is applied towards acceleration. It's going to start to accelerate and it's going to follow a torque speed curve. And eventually our machine will reach a settling point. It'll reach a point where its load torque and output torque balances, and that's going to be our operating point with that particular load. So in a non-controlled situation without a drive, this is a typical behaviour of an induction machine. It'll accelerate up and eventually it'll reach a point where its load torque equals the output torque. We also talked a bit about variations of load and how another useful thing about induction machines is they can be quite responsive to variations in load torque. So if we look at how this machine behaves, if we're operating at this point here, if our load torque increases, our machine might slow down a bit, but as long as it doesn't hit that peak of the torque speed curve, it can still provide the torque. If our load torque reduces, it'll get a bit faster, but again, it'll still find its sort of settling point. So we have a behaviour characteristic where it can basically perform at anything up to this peak. And this peak is commonly known as the sort of peak, but also the pull-out or breakdown torque, because that's the maximum possible torque we can get out of an already operating machine before it'll just fail to operate and basically stall out. And we can predict the position of that peak. We can predict that in terms of slip as rotor resistance divided by the root of stator resistance squared plus the sum of the leakage reactances squared. And we can also work out the torque we're going to get at that peak based on the voltage, the synchronous speed and the leakage reactances. So this is something we can actually predict, and it's quite commonly used as a simple sort of governing factor of how is this machine going to operate. Then we did talk a little bit about behaviours of torque speed curves and how actually things like rotor resistance make a big difference. Taking exactly the same machine but just varying the rotor resistance gives us the same peak torque in each condition but a very, very different performance curve. And actually having a low resistance gives us a very good performance in some ways in terms of having an operating point that's very close to synchronous, so having very small losses, but in other ways it reduces our starting torque, and we talked about how this has similar detrimental impacts on current, how we actually get much more starting current in a low rotor resistance machine than we do in a high rotor resistance machine. So although we'd like to design a machine with as low rotor resistance as possible for operation's sake, sometimes this type of machine won't start or it would trip its supply. And then we highlighted these in terms of efficiency, how that low rotor resistance fundamentally leads to a lower slip operating point, and that gives us less rotor losses and a more efficient machine. Then we highlighted the overall advantages and disadvantages of induction motors. So this is something, as I said before, you won't be asked to talk directly about synchronous motors, but it might come up that you'll be asked to talk about them with reference to induction motors. So some of the key differences in characteristics in terms of how they operate by induction versus how they operate by synchronous fields. You might be talking about operating points, so induction motors operate at any speed but synchronous. Synchronous machines, as the name implies, always run at synchronous. Induction motors take a lagging power factor, and they're generally lower power factor because we're always creating that magnetising field to link stator and rotor from our supply current. But they do have some good behaviours like inherent starting torque and easy self-starting without having to have any control. And so these are very commonly used industrial machines where you don't need good control, where you can just have something that does a fairly simple job. And they also work out as the sort of cheaper, simpler option typically because they're very simple and robust. They don't have complex moving parts. We also highlighted a couple of those tests. So we talked about how we can actually populate that equivalent circuit using that simplified circuit method. So we have two key tests we run to find all of those parameters. So we do a no-load test, and the no-load test is where we run our induction machine with no mechanical load. And if we run it with no mechanical load, our machine is going to operate at very, very close to our synchronous speed. So we're going to, if we think about it from the point of view of our torque speed curve, have a machine that's going to just keep accelerating. We've got no load torque, and eventually it'll end up very, very close to the synchronous speed at a point just representing the mechanical losses of the system. But if we do that, our slip factor is going to go down and down and down, our rotor branch resistance goes up, and so we can assume in the no-load test that our rotor branch resistance and impedance is more or less infinite, and what that means is we can simplify down our equivalent circuit to being just the magnetising branch there. So if we know the power characteristics there, if we know the supply, if we know the power consumed, we can then come up with real concrete values for magnetising reactance XM and our iron losses RM. Our second test we commonly apply for an induction motor is a lock rotor test, and this is a physical process where we lock that rotor, we bolt it down to prevent it moving, and that means we've set our slip as always equal to 1. So if our slip is always equal to 1, from the point of view of this equivalent circuit, in a lot of cases we can just ignore the magnetising branch because the vast majority of power is going into our rotor branch. Alternatively, if we've done the test in the order we're talking about, we've already defined the value of the components in that magnetising branch so we can calculate and discount them. But assuming they're fairly negligible, we have a very simple method then to work out the split of those. We can work out the sum of the resistances by taking the power consumed divided by I squared, and we can take the sum of the leakage reactances by finding the reactive power divided by I squared. We can find the resistance directly through DC measurement, so we can use a DC resistance test, whether it's star or delta. You can connect a DC resistance across any two terminals and work out what the resistance of each phase is. And if you do that, you can actually find the value of RS directly, and so you can find the value of RR directly. So those components we can find very, very accurately. The leakage reactances are a little bit harder to differentiate, so we typically just assume that those two are equal, that XS equals XR, and so we can represent those as the two parts. But using this methodology, we can then populate our whole equivalent circuit, and so we can get a model of how this machine's going to behave in any situation. We also talked about induction motors in terms of power flow, so how we can represent our machines in terms of power flow, and if we know the losses that occur in each stage, we can actually subtract those. So rather than working at it from an equivalent circuit point of view, we start out with a certain amount of input power, and we can just go along subtracting our losses until we eventually get to our output power. And this is also a useful kind of model, as we talked about, for when we're looking at thermal behaviour, when we need to know where those losses occur, because those all manifest as heating in our machine. And then the final part of the induction motor lectures was around starting and various performances. So there's a bunch of different ways that we can handle starting in induction motors. Some of them are quite simple, things like changing connection between star and delta. So this is something that's used in two ways. We can use it to increase the current through the three phases and get a high torque for starting. So if, for example, we want to start on a high low torque, we can use that to temporarily bump up our torque at starting. The other way we can use it is to actually reduce the inrush and reduce the supply. If the current we draw at starting is going to trip our supply, but we actually have plenty more torque than we need, we can do it the other way around to reduce the inrush current. We talked a little bit about how we can use that rotor resistance deliberately. So this isn't a technique that's used as commonly anymore, but we can vary the rotor resistance in order to give better performance. And in some cases, we do have external links to variable rotor resistance to do this. And then the more complex but more commonly used method we talked about was use of the skin effect. So taking advantage of the fact that we have a varying frequency in our rotor bars, ranging from at stall seeing that full frequency of the stator because the rotor doesn't move relative to it, and at our operating point typically having a very, very low rotor frequency, 1 or 2 hertz. And due to the skin effect, this can make a real big difference in the distribution of the current through our rotor bars. So we tend to design our rotors to actually take advantage of it. So for example, in this case, at startup, when we have a high frequency in the rotor, having a high rotor resistance top bar here, that gives us that high resistance characteristic for starting. And then in operation, where we have a low frequency, our current can happily spread through a large area of very good low resistance copper to give us a low resistance characteristic in operation. And if we do this right, this can give us a really good performance. We can go from having a good performance characteristic for starting in green and for operation in red, to having something like that blue curve that's giving us good consistent torque production across the board, and it's also giving us good behaviour, good starting, a good operating point. If we do it incorrectly, we can get some poor performance. We quite commonly have things like this, known as torque saddles, where we do actually have a little dip in torque, and we do have cases where machines can literally sit in that operating point, so reach a point where they can start up, they have enough torque to start, but not enough torque to get close to synchronous speed. So this is something that can happen. And one thing to bear in mind is that double cage rotors are very, very common for direct online sort of frequency fed machines, but they're somewhat unnecessary for drive controlled machines. So you do reach a limit with all of these starting and operation techniques where you just go, you know what, we actually need a drive for this, because that simplifies down the performance. You can get your sort of very, very good performance, low rotor resistance type machine and use that characteristic at more or less any frequency you want. So that's recapped induction motors. So those, between the sort of magnetic circuits and machine basics and induction motors, that covers 3 of my 4 questions. The final question I cover, the final area, if I just go back to it, since I seem to have dropped my link, is a combination of thermal effects and synchronous machines. So obviously Tianji taught you the synchronous machine stuff, but I'm just going to recap a little bit of it. So there is always a little bit of that in the exam, along with a little bit of thermal effects. But this is the material we covered last week. So we talked some about thermal limits, about power flow, the sources of losses and cooling, heat dissipation, and we talked about how we could model this. And then from the SRM point of view, Tianji taught you about the fundamentals of reluctance motors, their behaviour in terms of energy, the structure of them, concepts and types. So we discussed last week the thermal limits of materials. So we talked about winding insulation, how we have physical limits, but we also have that general lifetime degradation, how it isn't generally as simple as a pass or fail, 10 degrees extra, your machine's going to catch fire. It's a degradation in lifetime where every 10 degrees typically reduces your operating lifetime by 50%. So there isn't a fixed point, but you do have real impacts on lifetime of machines. We talked about permanent magnet machines, especially around that Curie point, and how good permanent magnet materials have real thermal limits around the kind of temperatures we often operate machines at. And then we talked about bearings, how because these have seals and lubricants, they also have mechanical tolerances that aren't suitable for thermal expansion. So bearings also have similar thermal limits. So all of these kind of set the operating temperatures we have in machines, but they also mean that we have to care about various points in the machine. We can't just look at the overall thermal side, we need to look at thermal behaviours at various points on the shaft, in the bearings, in the magnets. So we can deal with this in complex ways. So if you were at our guest lecture yesterday, Simon was talking about a lot of the different ways we deal with thermal management, how we deal with losses, and how we actually distribute these from our machines. We have some simple ways of representing these, which we'll cover in a bit. There's some more complicated fluid dynamic type ones, which we try and avoid if we can. But fundamentally, all this comes back to those power diagrams. So I've shown you one or two power diagrams for machines, and these are very important for thermal behaviour because these show us where our thermal losses are coming from. Pretty much every loss that we got in our various machine circuits, our machine models, manifests as some form of heat being dissipated into our machine, in the iron, in the stator and rotor copper, in the magnets, in the rotor iron, in bearing friction. So all of these heat sources appear in different points. We can define all of these losses, so we can define our magnetic losses as we've covered earlier. We can define our copper losses, and an important point to make is that copper losses are also dependent on temperature, so there's both a vicious cycle there where resistance increases as heat increases, but this is also a slightly painful fact that basically says your equivalent circuit isn't going to be the same at 20 degrees at ambient as it is at 150 degrees in operation. And then our mechanical losses, our friction and windage losses. So these are our different sources of thermal loss feeding into our machine. We talked about different cooling arrangements and how we have things that go from very, very simple natural convection dissipation into the environment to more complex systems with fans, to pumped water, submersible cooling. And again, I think Simon yesterday talked about some of the different industrial methods that have been used from very, very simple to very complex systems. But ultimately, there's a lot of different cooling arrangements depending on what the machine needs to do, what environment it's in. And fundamentally, all of our different heat dissipation methods can actually be defined down to a fairly similar equation, where we can say the thermal power flow is going to be based on a couple of key characteristics, including a thermal resistance and a thermal material potential. So what this means is that each of these components can be equated to electrical circuit terms. Just like we could handle magnetic circuits, we can do thermal circuits the same way. Our delta T equates to our voltage, so thermal potential equates to electrical potential. Our thermal resistance equates to electrical resistance, and our thermal power flow relates to current. So if we can actually define our thermal transfer across a given material, we can build thermal equivalent circuits for quite complex thermal problems using a few key elements. So we have a thermal capacitance that represents the ability of that material to store thermal energy. So that's our stored heat in a body of material. As we put heat power in, it's going to heat up. We have a source of heat, so in the motor context, that's going to represent those different sources of loss, our copper losses, our iron losses, our friction, and so on. And we have the thermal resistance, so where we have links between any two thermal volumes, we're going to have a thermal resistance. And we went through a couple of little examples where we showed how we can actually do simple calculations on these, and if we know the values of those, we can do calculations to work out the temperature at various points. We can work out how fast heat will dissipate and so on. And then we showed the more practical thermal motor networks, so how we build these up into much more complex networks where each component is represented in terms of thermal mass, its resistive connection to other elements. And although this looks complicated, solving this with a computer system takes very, very little time and gives us very good thermal models. So going on briefly to switch reluctance motors. So as I've said, this is what Tianji covered with you, but switch reluctance motors are machines that are relying on that saliency effect. So typically these are doubly salient in that we want a high degree of saliency on both stator and rotor to give us that maximum change in magnetic stored energy as the rotor rotates. And what this means is, as our rotor rotates, the magnetic circuit for our coil currents changes. So when our rotor is aligned with the stator poles, we'll get a good magnetic circuit. When our rotor is as far away from those poles as possible, we'll get a poor magnetic circuit. So we have a change in the magnetic circuit, and we also have a potential work and energy transfer which we can exploit to make a working machine. We can define all three characteristics in terms of energy. We can define our electrical stored energy, we can define our mechanical stored energy, and the energy stored in the field. And ultimately we can say that all three of these quantities must be in balance. And so if we fix our current and our speed in our machine, we can then look at the behaviour of these in terms of our torque, voltage, and flux linkage, or alternatively in terms of those three stored energy factors. And what we see is that in our simple two magnetic pole machine, we get a behaviour where we develop a torque as our pole starts to align, moving into that 90-degree point where we have full alignment, we have the highest possible flux linkage, and then as we keep moving that tooth away, we get the opposite effect. We get a torque that's now pulling that field back into alignment, we get an opposite point of voltage because we're now taking electrical energy back out, and our flux linkage reduces. And if we look at it in terms of energy, we're seeing effectively equal portions of mechanical energy and stored field energy represented by an opposite spike of electrical energy. So we're putting that electrical energy in as our tooth aligns with our pole, and that's giving us mechanical work and stored field out. And then as we move past that pole, we're going the opposite direction. We talked a little bit about sort of switching behaviours. So how, if we want to actually make this into a real operating machine, you can't just constantly activate those poles because, as we've shown, you get net zero energy, net zero force. So to actually make a working machine, we need some way to actually control the magnetic field, and ultimately we need a way to get rid of that stored magnetic energy in a way that isn't going to produce equal amounts of positive and negative torque. And this highlights a little bit about some of the challenges, although it slightly impinges on the field side of how much time you've got to get rid of that energy, how much stored energy you get, some of the issues there. And then it goes a little bit more into practical machines. So the two-pole stator, two-pole rotor isn't a very practical machine. And a more commonly seen system is something like this, an 8-slot 6-pole SRM. And in this kind of configuration, we have multiple poles because that lets us balance the torque contribution, it lets us produce force across multiple poles, so we get something a bit more like this, where we can produce something a lot closer to continuous torque due to the interaction of different poles, due to always having some kind of pole that's just coming into alignment, and so being able to produce something that's more like a constant torque. And you can define these just like any other machine in terms of power and losses. So you can define these chiefly around what losses they produce. So in the case of SRMs, because they don't have any permanent magnets, any current carrying conductors on the rotor, the key things we see are stator copper loss, stator core loss, and we also see rotor iron loss because the field is stationary relative to the rotor. And then the same lot of friction, windage, stray losses. So in terms of general characteristics, SRMs tend to be simple and robust, they're cheap to build, they don't use specialist materials, they usually have fairly low loss and high efficiency, and they're pretty fault tolerant, especially the sort of multi-phase types. There are a lot of configurations of SRMs that can be designed to operate in fault conditions where one of those phases fails. And they're also very temperature tolerant because we have no permanent magnets, no rotor windings, we can get potentially much higher temperatures in certain parts of the machine. But the chief issues with these are they have a low power factor. Because our force production is from stored energy, there's a fundamental limit to how much power you can get out of them, given that you're always balancing stored magnetic energy with output power. And they typically have high torque ripple, high noise due to that behaviour, as well as highly non-linear performance, which is quite hard to model and control. Okay, so that was a very quick run through of my material. So those are just some of the key points. So as I've said before, what I would suggest is you look through the material, don't rely on sort of recaps and slides, go through the material, use the past papers, but don't revise purely from past papers because ultimately they give you some examples, but they aren't the whole story. If you can answer the past paper confidently, you're in a relatively good position, but if you can do that because you've only revised the past paper, that's not so good. Okay, I think that's more than enough of my stuff. So Mark's here now, so if you want to hand over, I don't know if you want to give him a bit of time to absorb first, but...
Yeah, probably worthwhile having a 10-minute break.
Yeah.